Okay, hello to everyone, virtual and in person. Today we're very happy to have Eric, who is going to tell us about harnessing S-Duality in N=4 super mills and supergravity as SL to C average strings. So Eric, take it away.
Thanks a lot for the introduction and for reading the long title. Sorry, I know you're at a group meeting, you're just trying to relax, and so the long title is already a little too intense. But yes, thanks a lot for the invitation to talk and for letting me do it at this unusual time too. I noticed the announcement that got sent out yesterday said I was going to give a great talk. I didn't know I was signing up for that, so we'll see. But I hope I can live up to the standards. So good. So enough of the jokes. Back down to the physics. So I'll be talking about a work that came out in January with Scott Collier, a postdoc in Princeton, and some work in progress along these general lines. And so here are the pictures that hopefully by the end we'll be able to understand a bit more of. What the talk is about in words is a combination of ideas from three different areas. The first and maybe main part of the project was to try to understand S-duality in N=4 supergang mills in a new way. The second theme that this touches upon is the idea of averaging in holography, which will emerge in a new sense in the standard duality between N=4 supergang mills and NDS5 times S5. And finally, this will give us a kind of entree into general questions of statistics of CFT data in the space of theories more generally. So let me give a little bit of an introduction to these three prongs, and then I'll really give an outline for the rest of the talk. So to set the stage, we'll be considering 4D N=4 supergang mills with gauge group G. And this theory has a complexified gauge coupling tau on which generic observables depend. And so in particular, the imaginary part of tau is 4 pi over G Yang mill squared, which I'll just call G squared for today. This coupling is exactly marginal, and it parameterizes a conformal manifold that preserves the full N=4 superconformal symmetry. So I've pictured that conformal manifold M like so, where in this teardrop shape, where this cusp up top is meant to represent the free theory. And so these observables furnish a map between the upper half plane and this conformal manifold. Now I've highlighted the fundamental domain in the upper half plane under SL2Z because this theory enjoys S-duality. When G is simply laced, this is a self-duality of these observables under SL2Z transformations of tau, rather I should say of the theory. There are some global identifications that modify the statement for global extended objects, but we won't talk about that today. And so the point of view of the project of this talk is that S-duality of this theory is beyond a reasonable doubt, and we should try to understand its implications for the observables of the theory. So there's been, over the past 40 plus years, lots of evidence for the statement that N=4 is, in this sense, SL2Z invariant. A lot of these have been in the field theory context, computations of partition functions on non-trivial backgrounds, or d-instanton computations, or large N correlators, the spectrum of bound states and dyons, and so on. And this has only been bolstered by putting this theory in the context of ADS-CFT, where the string theory dual, for one thing, has its own SL2Z symmetry in 10 dimensions, which is preserved by the ADS5 times S5 compactification. And this is visible in the structure of graviton scattering amplitudes in ADS5 times S5, where, say, in the momentum expansion, you have SL2Z invariant functions appearing non-trivially. So, like I said, from the, let's say, bootstrap point of view, we'd like to understand what this symmetry implies about the observables of the theory. So when I say observables, to be a little more precise, I mean things that are non-perturbatively well-defined. That is to say, they are well-defined over all of the moduli space, and I'll call an observable O. And the SL2Z invariance of such an observable is the statement that under an SL2Z transformation of tau, it goes back to itself. So O for today is an observable, not an operator. And so it includes conformal weights, OPE coefficients, and say 4-point functions of superconformal primary operators. These are all SL2Z invariant when properly non-perturbatively defined. So we'll be trying to answer this question, and we'll make some progress toward it. And the idea in making that progress is to apply the spectral theory of SL2Z to this problem. That is to say, the harmonic analysis on the fundamental domain of SL2Z. One of the benefits of this tool is that it applies for any such observable O at finite n or large n. And I'd say one of the overarching messages of the talk is that it gives a new look for an old theory. So n=4, of course, is very well studied. We know many beautiful things about it. But as we'll see, once this framework is in place, there are some new non-trivial things that just kind of pop out with relatively elementary calculations. So I'm hopeful that there's more in the offing. One of the things that popped out was a sort of surprising appearance of ensemble averaging in this context. So, sorry, one moment. There's a beeping. Oh, good. So I'm in a room I'm not used to, so there are various beepings and sounds that I have to occasionally deal with. Okay, that's gone now. So good. So n=4 Supergravity is a well-defined setting for addressing certain general questions about CFT data. So here is a picture of the type you see in the conformal bootstrap, where crossing is solved approximately, and there are islands of allowed CFT data and regions that are excluded. And so one might ask, what are the statistics of the data within these islands of theories, either of theories or of the sort of crossing symmetric data that the bootstrap spits out? So we'd like to know, for example, as you vary in these allowed islands, how do things like operator dimensions and OP coefficients change? So in the context of n=4 Supergravity, we can phrase a version of this question by defining what we call the SL2Z ensemble, which is just a fun way of saying the space of n=4 theory is parameterized by this exactly marginal coupling tau. And so we can ask statistical questions about these OPE data as one varies over the moduli space. One thing that we discovered is that at large n, there's an interesting equivalence that emerges. In a sense, to be made precise, the strongly coupled planar n=4 theory at the level of the observables that I introduced earlier is equivalent to the large n ensemble averaged n=4 theory. And so what this means is different than some other notions of averaging that have appeared in the context of ADS CFT. The benefit is that it can be derived, and it has some similarities spiritually with these other ideas. And so, of course, I will talk about this at further length later. Okay, so that's where we're going. The rest of the talk is structured as follows. First, let me introduce this tool of the harmonic analysis, hopefully just introducing that which we'll need to understand the main points and no more. And we'll understand a few things about what this implies for the analytic structure of these observables, with one example given by a very nice object, which is an integrated 4-point function, which has been studied recently by, among others, Doragoni, Green, and Wen, which will give a very nice sort of clarification with this formalism. Then transitioning to large n, we'll study the structure of the TÜV limit, and that will help us transition to the statements about supergravity. Let me introduce some notation before proceeding. We'll call tau x plus iy. And so in particular, large Y is small g Yang-Mills. So large Y is the perturbative regime of the theory. And I'll write functions as functions of tau, but everything in sight should be understood to be non-holomorphic in tau. Okay, before I proceed, let me just say, please interrupt with questions anytime. I would say that ordinarily, but also this is a group meeting. So yeah, please ask whenever you'd like. Okay. So what is the basic statement? The basic statement is that if you have a square integrable, that is to say finite norm, SL2Z invariant function, this admits a unique decomposition into SL2Z invariant eigenfunctions, which form an eigenbasis of Laplacian on the upper half plane. So if we call this eigenspace L2 of F, where F is the fundamental domain, there are three subspaces. There is a constant function, there's a continuous subspace, and a discrete subspace. So I'll introduce these one by one, and then we'll get back to the physics. Okay. So the constant is easy. right? The Laplacian on the upper half plane annihilates the constant that has eigenvalue 0. This is also, for reasons to be explained in a moment, something we call the modular average. The second branch, the continuous branch, is the set of Eisenstein series, non-holomorphic Eisenstein series, with eigenvalue s equals a half plus it. So they obey this eigenvalue equation. Gosh. Sorry, this is getting a little too real. Okay. Good. Perils of working from someone else's home. Good. So the Eisenstein series obeys this eigenvalue equation. And so one takes the parameter s to be a half plus it. Okay, where t is just a real number. This is sometimes known as the critical line. And finally, there's this infinite set of what are known as Moss cusp forms, which again are eigenfunctions with eigenvalues specified by the spectral parameter Tn, which is real. And there's a discrete tower of these that goes all the way up to infinity. Okay. So to give slightly more detail, if we have some function O of tau, then we can write it in this three-part form where O bar is this constant term. Here's the integral over the continuous branch, and here's the sum over the discrete branch, where these overlap functions are coefficients in the expansion. And the inner product is defined with respect to the hyperbolic metric. Did I hear a question? Or?
I was just going to ask,
yes,
is there a qualitative difference between these e's and these phi's? What do they look like?
Yes, I'll answer exactly that in the next few slides.
Okay.
Including what they literally look like with the picture. Okay. Good. So the modular average is easy. This is just the average of O over the fundamental domain against 1. Okay. So hence the name, where we weight it by an inverse power of the volume, which you recall, despite being non-compact, the fundamental domain has finite volume with respect to this measure. The Eisenstein series looks like this. I've defined this so-called completed Eisenstein series, E star of S, by appending a factor of the completed Riemann zeta function defined down here, because this object E star of S obeys a functional equation, which is E star of S equals E star of 1 minus S. Okay. In the Fourier decomposition with respect to the real part of tau, the zero mode is a sum of two power law terms, obviously reflection symmetric under S goes to 1 minus S. And then the non-zero modes have this structure. This is some number theoretic Fourier coefficient, and the functional form is very simple. It's just a Bessel function. Okay. Not critical for what we're about to say, but here it is. And so writing the decomposition in terms of this completed Eisenstein series means that the coefficient function, the overlap, gets rescaled by 1 over that Riemann zeta factor. And this thing in turn has its own functional equation, which is why it's nice to write it this way. Okay. So you should think of this invariance of this overlap as a spectral version of the SL2Z symmetry of O. The other important thing about this overlap is that it can actually be written as a Mellin integral just of the zero Fourier mode of O. In particular, this last equation holds. This is known as the Rankin-Selberg transform. So if you know the zero Fourier mode of this thing O that you're branching, then you can construct this overlap and therefore reconstruct entirely these first two terms in the expansion.
Can I ask a quick question?
Please.
Is it true that is that true for any other spin component of or is it just specifically the zero mode?
It's specifically the zero mode.
Is it true? I mean, it's not going to be a Mellin integral, but is it true that a single Fourier mode will determine the full, or is it specific to the zero one?
It's specific to the zero one.
Okay.
Yes, it's specific to the zero one.
All right.
This follows from a nice feature of the Eisenstein series, which can be written as a Poincare sum, and then the so-called unfolding trick allows you to rewrite the overlap in terms of an integral over the real part of tau, which isolates the scalar mode in particular with that. So you're integrating O over the this interval with weight 1. Okay.
Right.
Okay, so the cusp forms, these are mysterious, and there's a lot of really interesting math here. Unfortunately, we'll have a bit less to say about the physics of them. They are functionally similar to the Eisensteins, but they don't have a zero mode. That's maybe the most important thing. So their Fourier decomposition looks like this. They start at mode number 1. Functionally, they have the same form. These are implicit Fourier coefficients ak of n for the nth cusp form. And so because of the absence of a zero mode, this actually decays exponentially at the cusp at large y. Okay. Remember, the Eisensteins had this power law behavior, which diverged at large y. This index n, I should have said, just labels this discrete infinity of cusp forms. Okay, so for successively higher n, the spectral parameter Tn increases, and it's known that they obey Weil's law growth, quadratic at large eigenvalue, but there's some discrete tower of these. And perhaps the key point about these functions is that while a lot is known about them, not a single one of these is known explicitly. By that I mean the Fourier coefficients and the spectral parameter are not known in some nice closed form for any single value of n. This ultimately can be traced back to the fact that these exhibit arithmetic chaos, which is a form of chaos which is arithmetic because of the niceness of the fundamental domain of SL2Z. It's an arithmetic group, and so the form of chaos that these things obey is somewhat milder than, say, random matrix chaos. But nevertheless, these functions can be thought of as eigenfunctions for this chaotic scattering problem, and that's why it's hard and so far not possible to nail down these numbers analytically.
Can I ask another specific question?
Yes.
So
please.
I'm a little confused about the statement of this arithmetic chaos because it involves the, infinitely many conserved charges and Poisson statistics. So it sounds a lot like integrability.
Yes.
So is it integrability or is it chaos? In what sense is it chaos besides the name?
So I hope to, on the next slide, I will show a picture which gives one answer to the question. But
Okay.
but I think that yeah, ultimately a lot of that behavior can be seen in the large eigenvalue behavior of these things. So there are various, as I've indicated here, various sort of chaotic properties or some conjectural that these things obey, which amount to saying that you can model these functions by taking random superpositions of Bessel functions, and so not only can you take them to be random superpositions, but in fact these Fourier coefficients ak are believed to be equidistributed with respect to the Wigner semicircle.
Okay. Yeah,
so that's one thing.
That does sound chaotic. Yeah.
So you can sort of say it this way. There's a semicircle law here, but the full infrastructure of the quantum chaos that we see in other settings, the repulsion, the sign kernel, and so on, that's not here. So it's sort of partial, but indeed chaotic. So
yeah. Well, the thing to say is that the semi-integrable are the eigenvalues because they're Poisson distributed. So it could be that there's some partial thing. The eigenvalues are integrable, but the Fourier coefficient are chaotic. This is what it sounds like.
Well, yes. So I agree morally with what you're saying. I think connecting this to the other notions of integrability n equals 4 seems not right. I don't think that. I'm not sure.
No.
Anyway, but
like
just to make, I didn't think so. But just to be clear, I think somehow the chaos is strong enough that we can't nail any of these functions down exactly, but weak enough that there are, Poissonian statistics governing the eigenvalues, and so it's somewhere in this middle regime.
Okay, sounds good.
Now at small n, when these conjectures don't hold, the sort of universality in the behavior doesn't hold, there's been some extremely precise numerics done to nail down, say, the first many hundreds of the Fourier coefficients for the first many hundreds of cusp forms.
Right.
So in the end, a decent amount is known, but one needs to interpolate between numerics and conjectures. Say. So let me show a picture for these functions. This is meant to demonstrate the difference between the continuous and discrete parts of the spectrum. Okay, so what have I done? I've plotted the square of a bunch of these eigenfunctions and projected to the zero mode and plotted as a function of y, the imaginary part of tau. So the red curve is nice and smooth. This is the square of one of the Eisensteins on the critical line. So I've just picked the spectral parameter t to be 1 for concreteness. And so you see this is relatively featureless curve. The other three lines are the squares of the first three lowest cusp forms projected to the zero mode. And these are, clearly wilder, more chaotic curves. The locations and amplitudes of the extrema are sporadic. There are no triple intersections, which is what you'd expect for a set of chaotic curves defined on a two-dimensional domain. And so I think this demonstrates a bit of what the difference is heuristically. Okay, so let me take a moment to connect this back to n equals 4. So the point is that in n equals 4 supergrading mills, the observables, which are functions of tau, are finite at all values of the coupling, except for possible boundaries of moduli space. That's true for any CFT actually, but in n equals 4, the situation is rather simple. We just have one boundary of this moduli space, the cusp up at tau equals I infinity, but that's where the free theory lives, and the observables converge to their free values there. So these observables are SL2T invariant, and because they are finite everywhere, they're square integrable, and therefore they admit the spectral decomposition. I'm emphasizing this because, well, this is one of the main points of the paper. I would say this technology applies, but also in a paper from last summer with Alex Maloney and Scott Collier, Liam Fitzpatrick, and Nathan Benjamin, we analyzed a similar problem for 2D CFT partition functions. That is to say, try to ask how this technology applies there. And that case is rather different because up near the cusp, 2D CFT partition functions diverge exponentially. But here, where tau is this exactly marginal coupling, everything is very nicely behaved, even up at the cusp, because that's just the free theory. Okay, so let's try to extract some consequences of this. In the n equals 4 context, the Fourier decomposition is the decomposition in total instanton number. So I've written it like so, where k, the mode number, counts the number of instantons minus the number of anti-instantons. And so we can ask, what is the structure of the instanton expansion in n equals 4 that's implied by this decomposition? The first thing we should do is impose the physical constraints on the problem and ask what they imply about these overlaps. One moment, let me take this phone and eject it from this room. This is getting a little too much. Okay. And even better, I've taken it off the hook, but please don't tell my in-laws. All right. Okay. So great. So the obvious thing to impose here is that there's a consistent perturbation expansion near Jiang mills equals 0. So that is a statement about the zero mode because the non-zero modes are exponentially suppressed at large y. And indeed, note that the cusp forms drop out in the perturbative expansion too, so we don't have to worry about the non-analytic properties of the lack of analytic knowledge of their properties. So here's the zero mode. There's the constant average term, and then there's the piece from the Eisenstein. So to develop the large y expansion, the strategy is clear. We deform this integral to the left and pick up some requisite poles in the overlap. So insisting that the right structure for perturbation theory be there, that is to say no logs and only integer powers of g squared, that is to say positive integer powers, tells us that the overlap has to take the following rather constrained form. There's a set of poles at integer values of s from here. And this, when evaluated on those integers, gives you the perturbative data for the theory, for the observable in question. This factor is just for convenience here. To this, you can add a function which we call fnp for non-perturbative, which has no poles and can only contribute in principle to non-perturbative, that is to say, instanton, anti-instanton terms in the expansion of O. These functions are rather nice. They have to be reflection symmetric on account of the reflection symmetry of this. They have to be real for real S, lest you get a complex decoupling expansion. And they have to be regular everywhere, except for possible poles at 0 and 1, which end up canceling between the two terms, so I won't explain that further. So this seems like a kind of reduction of the complexity of observables O at the level of the spectral decomposition. So let me take a couple slides to introduce an example of something that you can nicely apply this to, which is this so-called integrated correlator studied first by these authors, I believe. So take the 20 prime 4-point function, where the 20 prime is the scalar superconformal primary and the stress tensor multiplet. Strip off the part that is determined by word identities. You have the dynamical part of that correlator. It depends on cross ratios U and V and on the complex fed gauge coupling tau. And you can integrate this against a certain measure, which preserves supersymmetry, giving you some function Gn of tau, which is itself supersymmetric and yet depends on tau in a non-trivial way. This object also admits a definition in terms of a mass-deformed free energy on the force sphere, where one takes 4 derivatives to bring down appropriate integrated operators. These authors studied this at large N, and in a paper from about a year ago by Doragoni, Green, and Wen, they conjectured an expression valid for all n and tau, which is a very nice and compact expression. It takes the form of a lattice integral, where this integral kernel, Bn of xi, is just some rational function. So for example, for SU2, it's this rational function here. And the integrand otherwise just has this exponential factor. Now, on account of the lattice sum, this is manifestly SL2Z invariant. And the remarkable thing about this is that different values of n are related by a Laplace difference equation. So what does that mean? The action of the Laplacian on this thing can be rewritten in terms of a linear combination of the same thing where the value of n is shifted appropriately. So given the SU2 answer and the boundary condition that the SU1 theory is trivial, you can actually get all higher n just from SU2 by using this relation. So it's a very nice object, the integrated correlator. And just to make contact with what we're about to say next, there's another representation they wrote down, which is formal in the sense that it is not convergent everywhere in the upper half plane, which is as a sum of Eisenstein series with positive integer index with some coefficients C S of n, which can be determined by this recursion from the fact that n equals 1 is trivial, and n equals 2 answer is just this quartic polynomial here. So these two things are the same thing, at least formally, and it's clearly a very sort of tidy object. So motivated to try to explain where this formula comes from, we studied this in the spectral decomposition. And the claim is that it takes an extremely simple form in that language. Okay, so there's this first constant term, there's an Eisenstein part, and that's it. And the integral, the overlap for the Eisenstein part, is just these same functions, these same polynomials, C S of n, that I introduced in the previous slide. So for SU2, this was S1 minus S times 2S minus 1 squared. And higher n can be obtained by recursion. So this is extremely simple. The first thing to notice is that the cusp form overlap actually vanishes. The second thing to notice is that the non-perturbative part of the Eisenstein overlap also vanishes. Here we just have this pi over sine pi s part, which gives you the perturbative pieces, but there's not an additive regular piece multiplying the Eisenstein series. So this is, in a sense, functionally almost as simple as it gets. The two parts that are allowed to vanish both do. And the third part is just given by some polynomial in S, which is very nice. Indeed, for the SU2 case, we can read off from the result in the previous slide down here, that this fp of S polynomial is just 2S minus 1 squared. And for reasons I haven't completely explained, this is actually literally the simplest consistent possibility. It's reflection symmetric, it's entire, and it's non-constant. And those last two conditions I didn't explain, but they have to hold here. And so what is the simplest entire even function? It's a polynomial of degree 2 with no constant part. So this formalism kind of reveals some of the simplicity of this object that was hiding in this expression in the previous slide. In the paper, we also explain physically what this integral kernel is. It's a certain Borel transform of the zero mode of this, which is sort of tailored to the fact that this is SL2Z invariant. And these various nice properties of this kernel, which are observed but not explained in the original paper, can just be seen to follow from the SL2Z invariance of this object. So here I'm just trying to flash some of the sort of important points, but please ask any questions, of course, and more detail can be found in the paper. The one thing I'd highlight for further thought is that we don't understand physically why the cusp-form overlap vanishes. It's, of course, a nice object in that it's supersymmetric, but I don't think that's sufficient to explain this really nice feature. And it would be great to understand in the future what kinds of observables have vanishing cusp-form overlap and what kind don't. In the sense we talked about earlier, you could say that those observables for which this vanishes are non-chaotic, or at least less chaotic than those for which that's not true. But we'd like to sharpen that.
Eric?
Yes.
So you may have said that, or I missed it, but do you have a reason to be interested in this particular observable, or is it just an observable you want to use to test your harmonic analysis, or is there one way to see why you would want to focus on this observable?
Yeah, so certainly it was a nice, really comforting benchmark for us, because everything we said formally works and can be tested on this object. We'll talk a bit more about that later too. But I just was first compelled upon reading the paper by Doragoni, Green, and Wen, because it's an extremely compact result. So it's very rare, even in n=4, to have an object for which there's an explicit expression for all n and tau, whose size or complexity does not grow with n. So this is just, it's a single lattice integral. All that changes is the kernel. And moreover, the kernel can, at least conjecturally, be determined for all n by recursion from the SU2 result, which can be essentially engineered from the localization integral. So it's just a really beautiful object, even in the n=4 context. And so that's why I cared about it. But that's it.
And could you have guessed that so looking at the result, the old result, could you have guessed that the non-perturbative part was going to vanish?
Yeah, good question. So yes, so indeed, the non-perturbative part will not be there if the observable has no instanton, anti-instanton corrections to its perturbative expansion. So these are terms that are like e to the minus y times number. And in the original paper, they noted that the weak coupling expansion is asymptotic, but Borel summable. And typically, although not always, if you have a Borel summable series, then you don't need to supplement it with non-perturbative corrections of the type I just described.
Okay.
So they noted that these terms seem not to be here, and so we're just sort of couching that in a different language.
Okay. Thank you.
Sure. Any other questions? Okay. So back to some of the sort of abstract features of this decomposition and its use in n=4. In any CFT with a conformal manifold with exactly marginal couplings, we can define an ensemble average as an average over the exactly marginal couplings. So this is a kind of literal sense of ensemble average. And in those situations, there's a natural choice of measure, although not the only one, which is the Samologikov measure defined by the matrix of 2-point functions of exactly marginal operators, G mu nu Z, where Z is Samologikov. Okay. So given some operator O, depending on couplings, you can integrate it against this measure and define an average, which we denote with these brackets. So let's do this in n=4. It turns out that because of n=4 super conformal symmetry, the Samologikov metric is exactly the hyperbolic metric. So the modular average, which we defined earlier, which is to say the average over the fundamental domain, is the same thing as the ensemble average so defined. And because of that, the ensemble average appears very naturally in the spectral decomposition as this first constant term. So this suggests that there's something to be learned about ensemble averaged quantities in n=4 by studying the spectral decomposition of these quantities, which picks it out rather simply. If we go back to the previous slide where we studied this integrated correlator, you recall the constant term here is this n=1/4, and so we can just read off the average value of this quantity. So we're starting to approach these questions about statistics of CFT observables in this limited context, and the spectral decomposition seems maybe sort of intriguingly to be helpful for that. Okay, that of course will be a theme that returns later. So let's now transition to large N implications of this structure. Now in the TÜV limit, which we're all familiar with, the 1/n expansion perturbatively organizes into a genus expansion. You should think of this as an expansion of the zero mode because the non-zero modes are exponentially suppressed in N. And therefore, the same is true of the cusp forms. So again, in this limit, we don't need to worry about the cusp forms, which is nice. And we want to ask what happens in this limit to these observables. The algorithm is clear to do so. We again take the zero mode expression in general. You replace y by n and lambda using this. And then you need to understand how the overlap behaves at large N. Now, there's a simple scaling argument that tells you this, in fact. And it leads to the following expression, which is somewhat schematic. I'm suppressing some coefficients just to make the physics clear. And I am turning off this NP part of the overlap. So we just have an observable like the integrated correlator, say, where the Eisenstein overlap is especially simple. Okay, so there's no non-perturbative corrections of that sort. So what is this expression? Well, here's the ensemble average. Here's the sum over genus. Here's the integral. We have just the FP part. So this is this set of poles and the coefficient introduced by definition. Here's FP at genus G. So this FP, the overlap itself, emits a 1/n expansion. Then there are two terms here. Each of them comes from one of the terms of the Eisenstein zero mode. Think of it that way. So remember that zero mode was like a y to the s and a y to the 1 minus s. Each of those terms ends up leading to one of these terms. And this is actually a pretty rich expression. And at first it seems like kind of a weird expression. So the claim is that modulo having turned this off and suppressed coefficients, this is the most general form of the TÜV limit of some observable. And the first thing you might notice is that there is an n here. Okay. So we've written the genus expansion where the n's are appearing out front, but there's also factors of n appearing here. The first term looks nice. That would give us the lambda dependence of this observable. But the second term looks a little strange, but it has to be there because of SL2Z. It's the sort of partner of the other term. Now, because we're expanding at large N, we need to deform the contour to the right and pick up the requisite poles in the integrand. And so consistency with the genus expansion, with the fact that this whole thing admits an expansion only in powers of 1/n squared, and say not 1/n or any other funny power, tells us that this object here has to have poles at these half integer values of s, and only there. Otherwise, you would violate the genus expansion. So that tells you something interesting about the polar structure of this. And in turn, because the same function here is determining the strong coupling behavior of the function by way of deforming this term to the right, you learn something. So the first thing we learn is that there's a large N diagnostic of instanton anti-instanton effects. That is to say, when this FNP function must be there. If you have an integer power of 1/lambda at strong coupling, well, that couldn't have come from this for the reason I just explained. So this function must be responsible for that. The second thing already mentioned as well is that SL2Z seems to rearrange the 1/n expansion. So if we look at strong coupling, what this gives us, this first set of terms is the powers of 1/lambda that you get. A and B are both coefficients. And then there's the second set of terms, which are the ones that look kind of strange. They come in even powers of 1/n squared by imposing the previous condition, with positive powers of lambda. Okay, so if we sit at a fixed genus, say G equals 0, there's an n squared out front. But then the claim is that there are subleading powers of 1/n squared that you should associate with the genus 0 part of the answer. And these also come with positive powers of lambda. But it turns out that this is natural in the context of strong coupling and ADS CFT. You should think of these as a kind of renormalization of the sort of leading tree level genus 0 action. So for example, in the bulk, there's a one loop R to the fourth term in ADS fashion S5. And if you translate the scaling of that term into field theory variables, you find this. So this is just the genus 0 m equals 0 term here. In the bulk, this is one loop, but you should really view this as part of the genus 0 CFT data. That is to say, given the leading order answer, in the 1/lambda expansion, if you were to expand at 1/n at large lambda, you would get something which diverges, but you should think of this as a kind of renormalization effect, a cutoff at the string scale of 1/n loops given the leading order answer. And so the genuine lower genus data, or rather higher genus data, is finite and can be studied sort of without having to worry about these problematic divergences. The last thing I'll mention that sort of follows just structurally from this expression is that if you have non-perturbative effects at large lambda, then you also see there are non-perturbative effects at large n. So why is that? Well, where do the non-perturbative effects in large lambda come from? If you expand this integral by, if you rather analyze this integral by deforming this term to the right to develop the 1 over lambda expansion, you will need non-perturbative terms if the resulting series is asymptotic and say non-Borel summable. And that's a statement about the asymptotics of this function where s is taken to positive infinity. But then you also have this term coming along for the ride. So when you have e to the minus lambda terms, so you'd have e to the minus n squared over lambda terms from here. And those are non-perturbative in n. This is pretty natural from the point of view of the bulk. If you study this a little more carefully, you see that the characteristic non-perturbative scale of these strong coupling effects in lambda is given here. And these other terms that come along for the ride come along with this scale. And so what is this set of scales in the bulk? Well, root lambda is just the fundamental string tension. So these should be thought of as fundamental string world-treat instantons in ADS5 times S5, where I've just pictured them schematically here, borrowing a figure from this paper. And so what is the statement? The statement is that, well, because of S-duality, you also have D-string instantons. So that makes a lot of sense. What this shows you is that when you have the one, you necessarily have the other, which in retrospect is something you might think about that you might have figured from S-duality, but there are not many discussions of D-string instantons in the literature, so this seems like a kind of new way to see this. Okay, so let's get back to the averaging. Those were some features of what happens in the TOEFL limit, but perhaps the main feature is something that I sort of didn't say explicitly, but is visible here already. At strong coupling, both of these terms die off. Right? This is suppressed by 1 over lambda, these are suppressed by 1 over n, and all that's left would be this term here. If you generalize this to include FNP, to give the most general strong coupling expansion, you see the same kind of structure. And what you get, for example, at order n squared is the following thing. You get a constant term, which is the leading term of the average at large n, the order n squared piece of the average, plus the subleading terms in 1 over lambda. So this is a lot like the usual expansion we develop, except the infinite lambda piece is also identified as the leading term of the average. So you derive an equivalence between strong coupling and ensemble averaging in this large n sense. And of course, you can rephrase this holographically like so. So once we've written that equation, it's kind of deceptively simple. This just falls out right away. And well, there you have it. So lest this seem kind of quick, let's test this on the integrated correlator. In the TOEFL limit, it was computed by these authors to have this expansion. In the spectral decomposition, we can extract the ensemble average easily, and that was this term here. So indeed, at large n, there's an equivalence as claimed. Let me mention something which is perhaps useful for intuitively understanding what's going on. Sometimes people say, well, at large but finite n, if you imagine computing lambda, that is to say g squared n, as you vary g squared n is large almost everywhere on m. So the average doesn't seem to do much, you just get the same large lambda answer, and maybe that's why the average is the same as the large lambda limit. Now, this turns out to be correct, as we showed. This doesn't actually get you there. Let me just walk through this a little bit carefully to make sure we're treating our limits properly. So this is not strictly legal reasoning, because at finite g, one is not in the TOEFL limit. So instead, the relevant statement should be made at large n and fixed tau. And in this limit, observables take the following expansion. There's the order n squared piece, the supergravity piece, with no dependence on tau, followed by terms that are suppressed by 1 over n, each of which comes with an S2 invariant function of tau. For example, this might be the E3 halves Eisenstein series, if you're familiar with this kind of expansion. And so if you took this expression and you imagine averaging it, this suggests that the leading order answer should be supergravity because the leading order answer has no tau dependence. So the normalized average would just give you 1. That itself is not well defined either because these functions have divergent averages. So up at the cusp, they behave like power laws. And so when you integrate them, they will diverge. So you can't take large N first and then take the average. But it turns out that doing a rigorous calculation, in our case, using the spectral decomposition, gives you the same answer you might expect from this kind of logic. So to summarize, morally, when you're at large N, every point on this manifold looks like it's at strong or let's say very strong coupling. And so averaging ends up giving you back that strongly coupled answer. So this is, in a sense, kind of mild, but has the virtue of being true, which is nice. Okay, so let me make some comments, and then I'll pause for questions and feel free to interrupt, of course. The first comment is that the traditional holographic correspondence still holds. We're not claiming that we should replace n equals 4 by any sort of averaged version in order for ADS-CFT to make sense. It's just that this average is emergent at strong coupling in large N, and can be identified with the strongly coupled theory. Like in lower dimensions, the averaging gives a simple, that is to say, extremal bulk dual with the sparsest spectrum consistent with the symmetries. There's a version of this that actually extends to all orders in 1 over n. The correspondence there is that if you take the genus G part of the average at leading order in large N, this is equal to the strong coupling limit of the genus G part of the observable. And in order to make this precise, it was important that these renormalization terms I mentioned before had to be subtracted so that the genus G observable O at large lambda is actually finite, just like this would be, since this is just a number in the 1 over n expansion of some function of n. The last comment I want to make is that it introduced a new possible conceptual strategy for extracting supergravity from the CFT, which is to say, instead of computing strongly coupled planar quantities, try to compute large n limits of averaged quantities. So you can imagine that there might be some way to compute averaged quantities as functions of n, and then the large n limits would give you the supergravity answer that would be the same thing as a strongly coupled limit. This maybe is not feasible, but one reason that this seems worth thinking about is that in Narayan CFTs in 2 dimensions, it was recently proven that the average spectral gap is of order C, but it was proven not by studying holographic limits of individual Narayan CFTs, but by deriving the average gap and using the fact that the measure over this moduli space is positive. And so the typical theory has this gap, and therefore it is possible to have that gap, right? So is there some way to compute averaged quantities in n equals 4 directly and then infer these types of statements from that? That would be nice. So let me pause and ask if there are any questions. Okay. And let me also ask about time. Do I have something like 10 minutes left?
Yeah, sure. Started a bit late, so
Okay, great.
take your time.
Great, thanks. All right. So trying to understand this physically has sort of led us to the picture that supergravity is emerging as a kind of average. And so this motivates us to study the statistics of the SL2Z ensemble a bit more. As I tried to explain earlier, I think this is interesting, not just vis-a-vis holography, but as a question about theory space in general. And so returning to this kind of caricature for a moment. Yes, yes.
Sorry, I didn't realize I had a question.
Please, yeah.
So is there a sense in which this whole story still exists if you deform the measure?
That's a good question. I would think so, because the intuitive argument we gave earlier really did not rely on that, right? So the answer, the claim is not that the sort of answer is coming from some localized effect up the cusp exactly. It's kind of sort of coming from everywhere. And so if you change the measure in some smooth way, I wouldn't imagine this to have some large effect. It might change the subleading orders, but I would say the short answer is no. It seems pretty insensitive to the measure. And maybe one could say the main benefit of using that measure is that we can actually sort of, extract this rigorously from the spectral decomposition, where it's the hyperbolic measure in particular, it's the modular average, which one is computing. So if you're interested in an average with a different measure, I don't know sort of how to extract this statement, although I would imagine it to be true based on the physics argument we gave before.
Okay. Thank you.
Sure. I'll talk briefly at the end about possible generalizations to other theories where, most of the time for theories with conformal manifolds, we don't know the Zamenhof metric, even in what you would call nice examples like 4D n=2 superconformal theories, where the measure is in some cases determined by a localization integral. That's explicit on the one hand, on the other, it's not what you would call simple necessarily. So we'd like to be able to extend this to other theories, but there's a kind of technical challenge in making rigorous statements, but I expect it to hold. We'll discuss that later. Okay. So the kind of question we want to answer, in general, CFTs in theory space, or sort of space of bootstrap equations, is a statistical question about these data. Okay. So the idea of a CFT ensemble, well, this has been sort of turned over in various ways and is still being considered in various dimensions. And it's an interesting one, but one can take a very literal interpretation of this term to be defined by a space of CFTs which have exactly marginal continuous couplings. And so that then still begets various interesting questions. One of them is, what are the statistics of the ensembles defined by these conformal manifolds M? How do these statistics relate to the other properties of M? Say, if the conformal manifold is compact or non-compact, is this somehow visible in the statistical properties of the OPE data? And just completely generally, what are the large N systematics of these averaged observables? So the SL2Z ensemble gives us a good starting point to answer some of these. And as a warm-up, let's consider the large N systematics of the average of O itself. So we're not really doing statistics yet. For simplicity, let's take FNP to be 0. The reason is just that the point I'm about to make becomes a little more striking, but it generalizes when it's not 0. If you take the average and expand it in 1/n, the average proceeds in integer powers of 1/n. But this is different from the 1/n expansion of the unaveraged quantity, which proceeds in half-integer powers. So somehow the averaging is producing a different large N counting for you. And I'm viewing this as a kind of unobvious and, to my eye, interesting property of the average quantities at large N. You can't just read off the large N systematics from the unaveraged quantities. Somehow the averaging is doing something non-trivial. So let's look at the simplest probe of statistical correlations, which is the variance. So let's take an observable O, square it, take the SL2Z average, and then subtract its average squared. This, of course, is just a 2-point function of O minus its average. And we want to spectrally decompose this. So we're doubling the theory, studying this quantity, and viewing this as the average of a 2-point function of O spec with itself. There's a nice way to write this in spectral language. You insert a complete set of states, as it were. This is usually known as Parseval's theorem. And you get a nice expression. You just take the spectral overlaps and square them and add them all up. So to say it a little bit more fancifully, the second moment in tau space, that is the variance, is equal to the second moment in spectral space. We square the spectral overlaps and then we integrate. So we can take this expression, which holds completely generally, and expand it to large N using the properties of the overlaps for the N=4 problem we're interested in. And if you divide out by 2 powers of the average, you find that it's 1/n suppressed with a simple coefficient given by the genus 0 part of the overlap, like so. It's 1/n suppressed This is small, therefore, but it's not that small. We'll return to that in a moment. But first, let's check the formula. So our friend, the integrated correlator, gives us a way to check this. On the one hand, we evaluate this and stripping off numerical factors and the n cubed here. Remember, because average of O goes like n squared. We get this integral. You can compute this numerically. If anyone knows how to do this analytically, please let me know. We get this number here, and we plot this as the dotted line here. And you can compare this to a direct calculation for finite n, starting from 2 up to, I think, 107. And we see that it asymptotes nicely to this line. So this formula is therefore, at least as far as the integrated correlator is concerned, correct. It checks out. And so now returning to the conceptual point, this analysis sheds a light on the sense in which we can say gravity is self-averaging. The SL2Z ensemble is self-averaging at large n because the variance is suppressed, and the large n average is supergravity. In other words, if you take any member of the ensemble large n, these observables O of tau are well approximated by their average, up to 1 over n corrections. That's what self-averaging is taken to mean here. Now, the obvious thing to make contact here with here is other ideas about ensemble averaging in gravity, where you don't have exactly marginal couplings, and one is trying to understand why things appear to be ensemble averaged when there's no literal average over couplings in sight. So if we compare this to the statement, for example, made by Schwenker and Witten, that can be characterized as saying that gravity reliably computes quantities which are self-averaging in large n random matrix theory. These are different statements, but in the context of n equals 4, both appear to be true. And it raises the question of whether the SL2Z ensemble has an RMT structure hiding inside. I don't know the answer. I would caution against drawing quick conclusions. I think the answer seems like more no than yes so far, and we're studying the non-perturbative effects to try to get a handle on this. But this is the sense in which holography in NDS factors S5 seems to be self-averaging in the language of today's talk. And just to stress, of course, here throughout this whole talk, we're finding that unaveraged quantities at large n can be identified with large n average quantities. But here in this discussion, it's meant to be totally general, where one is asking why things appear to be averaged, even when there is no averaging being done, at least not manifestly. So one can study non-perturbative effects in this ensemble. We did this a little bit in the paper. This is still work in progress, to be sure. Let me just stress a couple overarching points. The variance has 2 layers of non-perturbative effects. The first are effects at fixed genus, and the second are effects that would arise from a sum over genera. So the fact that there are effects at fixed genus is related to this point before, that even at fixed G, you have this 1 over n expansion of these kind of renormalization terms. This is morally the same thing. And in the paper, we discovered that there are non-perturbative effects at scale e to the minus root n times a number. The integrated correlator has these, for example. The sum over genus is more complicated. We're still trying to understand this. Preliminarily, it seems the sum can generate scales e to the minus n times a number. And it's possible that there would be doubly non-perturbative effects if the sum over if the genus sum over these is itself asymptotic. We haven't determined whether and when that actually happens, but it actually seems to be a kind of rich problem, which would be nice to understand more. So we're trying. So what does this have to do with the bulk? What about wormholes? I don't see an e to the minus n squared, you might say. And neither do we. But I just want to make 2 comments about what I think the interesting questions are, and then we'll be close to the end. There are 2 interesting independent sets of questions, I think. The first is, what are the averaged string duals to the 1 over n corrections of these ensemble average quantities? In other words, is there an effective description of the average string theory? Recall that the average had this funny 1 over n counting, which is not in the Tuftian 1 over n squared expansion. Right? There were these 1 over n corrections to averages and variances and so on. how do you recover this from a kind of averaged bulk string theory? It's not something that you can understand before averaging because the bulk quantities don't admit that systematics. And the second question is a bit sort of more ambitious, I might say, which is how much does the unaveraged bulk string theory know about these statistics? Does the variance we're computing somehow contain bulk space-time wormholes? The answer is definitely not obvious because of the fact that it has 1/n scaling as opposed to e⁻n² scaling compared to the squared average. And so there are various puzzles about this. We made some comments in the paper, but I think the verdict is certainly out. And I don't know if, what exactly even the space of solutions or near solutions in the bulk is that one would like to match on to this statistical property, but the question should certainly be investigated. Last comment I want to make before concluding is, well, we expect this to generalize to other instances of ADS-CFT, where there are exactly marginal couplings. And the general story should be something like that the ensemble averages over conformal manifolds, or at least subspaces of these submanifolds, localize onto supergravity at large n. Right? That's what we saw for n = 4. And the intuition suggests that this should be true in other situations like that. But when you have more than one coupling, there are lots of choices to make. So it's hard to come up with the exact prescription. Let me just demonstrate this with the case of the D1, D5 system. We talk about, we articulate other logical scenarios in the paper, but the scenarios basically boil down to the following two. So in ADS3 times S3 times T4, we have a bunch of moduli. There's a generalized S-duality symmetry. And at large C, we know that there's a TOEF type coupling, which interpolates out to supergravity, right? There's some direction G, and so G times root C forms a TOEF coupling, and a large TOEF coupling, you get out to supergravity. So what kind of average would land you on a supergravity theory in the same way that we saw for n = 4? Well, there are two sort of natural possibilities. The first would be to perform an average over the entire conformal manifold. And the second would be to perform an average only over the so-called gravity direction G, that is the coupling which is ultimately responsible in the TOEF limit for taking you out to supergravity. So this orthogonal direction is spanned by these other moduli, which just come along for the ride and are there in the bulk as scalar fields. I don't know what the answer is to this question, but there are two different possibilities. In particular, the first possibility averages over everything, including the other moduli. So another way to say this is that you're also averaging over the bulk. Right? The bulk has all these 20 scalar fields. So if you average over everything, you're kind of doing a bulk average, not just a boundary average. Nevertheless, you could ask if the result is a simple theory, some kind of consistent truncation. That would be interesting. But maybe spiritually, the second option is closest to what we saw in n = 4, where you average over the coupling, which is responsible for the gravity dynamics emerging, and then you ask what happens. Actually doing this in this case, I don't, that is hard. It's a 20-dimensional moduli space. Who knows what the measure is that you should use, but maybe it doesn't matter so much. Okay, so that was the last comment I want to make. Here's a summary of the talk. There are various future directions. I won't go down the list one by one. Let me only highlight that I think there's interesting stuff to be said about these statistics, which would be a nice toy model for these more general questions. And it would be nice if we could interface this with bootstrap techniques to get more analytic handles on averaged quantities in CFT. So let me conclude there. Thanks.
Thanks, Eric, for a very nice talk. Do we have more questions?
I guess maybe we'll ask a general question. So maybe you've explained this a bit, but I think I'm not completely understanding whether. So you have this equivalence with the averaged and the large lambda quantities, and so you could. I mean, I guess one thing you could say is that okay, that holography naturally relates the gravity side, the supergravity to large lambda, and that happens to be equal to the average. Or you could say that supergravity naturally relates to the average, and that happens to be equal to large lambda. Is there a way to distinguish those two?
That's a fun question, because we're we're very used to just thinking of the two sides as one and the same, without such deep ontological differences. But which one the average is kind of more capturing, so to speak. I would say that,
I'm asking basically, could it be the average? It just happens to be equal to the thing that is dual to supergravity, or should I really take the equivalence between the average and supergravity is telling me something important about the relation between averaging and effective gravity emerging, or is it just?
I'm not sure about that. That's one of the big questions, I would say. I'm not so sure. I think for that, because here we should distinguish between the types of averaging that are being talked about in this context, and the big question we would want to answer, I would say, is in any dimension, whether or not you have free parameters on both sides, and if you do, you just fix and identify them like we normally do in CFT. Why is it that even after doing that, there are things that seemingly can only be explained by a form of averaging? And so we're not answering that question because our construction relies on the exactly marginal coupling, and we're taking the sense of averaging in the literal way. The fact that it ends up giving you the supergravity answer, maybe it suggests that these two types of averaging are not necessarily that different, but it would be nice to make that more precise, more quantitative. So I would say I'm not sure how much we're learning about the most general puzzle from this point of view. To use the language of Schlenker and Witten, it's the apparent averaging that one wants to explain, and that shouldn't have anything to do with exactly marginal couplings, because there might not be any. But somehow the fact that this is happening, I'm not sure if there are completely general lessons for things like the 2-0 theory and so on. But it does seem like we have a situation that we can study quantitatively, where we know that some version of this is true, and that I feel might be a jumping off point. But it's not clear how much is specialized to this context and how much isn't.
Yeah. Thanks.
That is perhaps related.
Yes.
So are the first the first stringy corrections going to essentially resolve a bit of that? Because you might ask, I need like an average string theory, or just a single string theory. Right?
Well, I don't think they can resolve it in any. Sorry, I thought you were done. The audio was a little funny. I don't think that can resolve it. The way one should, the way to think about the emergent average is that once you start including alpha prime corrections, those are mapped to the 1/, lambda corrections in the usual way. And the point you're perturbing around is the point that can be reinterpreted as an average, but the perturbations, are mashed on both sides as they normally are. But still, there is the structure of the full string theory becomes important once you go beyond the leading order. So let me go back a slide, a few slides. So let's look at this formula, for example, for the variance. The variance involves these squared spectral moments. And so these moments, these overlaps involve more than just the averaged answer, right? They're functions of the spectral parameter. So what that ends up translating into is the statement that beyond the leading order, you get not just supergravity data entering into the expression. And so that's why I think when we're trying to understand the answer to this first question, this somehow should involve the full string theory. But this might suggest that there's not much to be learned about effects in the supergravity approximation. But I don't really know. I think that may well be true, but it still should be an interesting question to understand what average string theory looks like. And then the statement that, right, this ensemble is that gravity is self-averaging in the sense articulated here, means that you're connecting to gravity sort of whether you like it or not, because the point you're perturbing around is the supergravity point, right? So in other words, it's not put in by hand that, you know, the large n limit of the average is the supergravity regime. So therefore, when you're studying the 1/n systematics around the large n limit of this ensemble, you're studying somehow some perturbative expansion around gravity, but in this ensemble sense. It's a bit confusing, honestly, but I think some of the meat of the answer should lie in the subleading corrections. A leading order of the answer, this correspondence seems to be not, you know, there's not so much to play with. It's just a number you're matching. But the full string theory should be relevant when you're computing these kinds of corrections. And ultimately, whether that reveals something about the way gravity works in other settings or not, I don't know. But I would say this is one reason to be skeptical that a general explanation for space-time wormholes should come from this point of view. You know, in addition, the fact that this scaling appears. Maybe the wormholes are hiding in exponential effects inside the variance, but you still would have to explain what the map is between this non-perturbative effect in the ensemble and the bulk. I wish I could give a clear answer, and maybe that was too long. But
so just to be sure, I understood. So one of your claim would be that all variances go to 0 at large n.
When you say all variances, you mean for any observable O in this ensemble?
Yeah, I mean, well-behaved observables, yeah.
Yes, yes. So when normalized by the squared average, yes. There's a sharp, you know, the distribution is sharply peaked around the supergravity value, let's say.
So you predict, so if all Sugra observables can be described as limits of these observables, then you predict that there's going to be no wormholes in supergravity.
Well, so that's the part that that I wouldn't feel comfortable saying, because the wormholes could appear as very subleading effects here. You might ask, well, where's the leading? I mean, it's a mystery to understand the leading effect from the bulk point of view. Mm-hmm. The fact that you have this 1/n suppression, what is this in the bulk? It doesn't have to be related to something in the unaveraged theory, but perhaps it is. But if it is, then it's not a usual perturbative fluctuation. This is like, right, some root G Newton thing. And of course, root G Newton effects do appear in various contexts of entanglement phase transitions and so on. But I'm not sure what even the bulk interpretation of this would be. And then following that, if you could try to understand exponential effects in the variance in terms of bulk space-time wormholes, that would be nice, but there's something to do first. So yeah, it's definitely not clear what the relation should be between those two things. But what one can say is that there's a form of, I mean, there's a kind of mild form of the, you know, questions related to factorization that this is shedding some light on, which is, if we double the boundary theory, we have some factorized observable, why is it that when you write an expression for that observable, there's a piece that appears to correlate to two copies? And the spectral decomposition is giving a kind of answer to that, because the modular and ensemble averages are identified. And moreover, at large n, when you have a single copy, that's the gravity regime. So that's why this seems like it should have something to do with gravity, but that's where it becomes fuzzy.
Are there interesting things to say if you look at Wilson loops or more non-local things?
I bet there are. We didn't do that because we restricted to purely SL2Z invariant observables. If you look at something like that, then those things are invariant under, say for the SUN theory, they're invariant under a congruent subgroup gamma naught of n.
Mm-hmm.
And so one would need to develop the spectral decomposition for that. And that's possible. That is known. So essentially for each cusp of the congruent subgroup, you have an Eisenstein part of the decomposition, and then there's cusp forms to add to that. Of course, not that much is known about those, just like in the SL2Z case, but one can write down formally what this looks like. So I think that would be nice to do. Yes.
Mm-hmm.
And there also are various expressions to try to match to and make use of there.
Yep.
Yeah.
Okay, let's thank Eric one more time.
Thanks. Nice
Thanks a lot.
talk.
Thank you.